All right, this is video 4 in the baby real analysis series. And in this video, I'll discuss the concept of Supremum and Infimum. And it's been mentioned before that over and over in previous videos that the real numbers is an ordered field. But the real numbers is more than just an ordered field. There's this sort of special property that delineates it from being just an ordered field, and that property is an axiom called the completeness axiom. And to think about that, as far as what this does, is we're going to use the rationals to identify all of the irrational numbers, as far as for what this completeness axiom is going to entail. And as an example, let's consider the set A equals the set X that are rational, such that X squared is less than 2. If you were to plot this on a number line, so I have the green dots are the rational numbers X. So this is all A, and each of these is the value X that lies in that set. And so we have these gaps in between, so it wouldn't just be the entire line shaded because we're only dealing with the rational numbers in that interval between, and it's approximately negative 1.414, that's, and then approximately 1.414 for the endpoints, basically square root of 2 and negative square root of 2. Now on the right, you have these orange numbers like 1.5, 2, and 6 that are more than square root of 2, or more than 1.414. So since they're more than the square root of 2, and they're not in the set A, they're bigger than all of the elements in the set A. And so these orange numbers like 1.5 and 2 and 6, these are examples of what's called upper bounds. And among these upper bounds, there's what's called a special kind of upper bound, and it's the smallest or least of these upper bounds. And this is called the least upper bound, or the supremum. And the bound in this case is exactly square root of 2, which is an irrational number. So we have the square root of 2 being our supremum. So that's our sup of A is square root of 2. And that's the notation we use. So sup of A is going to represent the supremum of some set A. And then a supremum is the lowest upper bound of the upper bounds of A. So the square root of 2 is the lowest value that's an upper bound to our set A, where A is the rational numbers that whose square is less than 2. This is the least upper bound. All right, and in this case, we have an irrational number, square root of 2, that's our least upper bound. And that's how we can sort of define an irrational number as these upper bounds, least upper bounds to some set. So in order to get all of the real numbers, we start with the rational numbers, and then we add in all these least upper bounds from all the sets that are bounded above. For example, like our set A. And then we include the square root of 2 in our set of the real numbers. Doing this for all such sets similar to A, which are bounded above, make the real numbers complete. Okay, and then we don't have to have the irrational numbers be of the form square root of some number n. So they don't have to be all of that form. Like we know that pi is a irrational number, and like e is an irrational number. There's probably a lot more irrational numbers that are not of the form of this, where you take the square root of some value. Right, so this was just an example that we are just demonstrating that in this case, the square root of 2 is the supremum of the set A, where A is the rational numbers whose square is less than 2. And the supremum is the least upper bound of the upper bounds of A. And if you have the rational numbers, a set of rational numbers, and you have it to where you have these sets that are such like A, and then you have these least upper bounds of A, we include these least upper bounds in the set of real numbers, which makes the real numbers complete. All right, so I just drew this over again, and again, we have the green dots, so the rational numbers that are in A, and then we have square root of 2, which is the least upper bound of A, and so we include it in the real numbers, and all the orange stuff that's shaded are the upper bounds of A. All right, so to make things formal, we're going to go over a good bit of definitions. And in the following video, I'll do more examples making use of these definitions. So let S be a subset of the real numbers. B is called an upper bound of S if and only if, for all S and S, S is less than or equal to B. And then C is called a lower bound if all S and S is greater than or equal to C. And so if I have my set S, and let's say I sort of have this, and this would be like our B, and then everything in S, all of this. So for all S and S, these values are less than or equal to the value B. And so that's our supremum, or the, or that really that's just an upper bound, but I could also have B be something else. Like for instance, I actually drew what the supremum was, but this could be B also. So this is an upper bound because it's larger than all the elements in S. In this case, I already drew this B is the least upper bound. And then we have a similar thing with lower bounds. So anything that's sort of out here, these are like my values C, where for all the elements in S, all of the elements in S are greater than or equal to C. All right, those are my lower bounds. And then we say if the set S has an upper bound, then it's bounded above. And if the set has a lower bound, then it's bounded below. All right, so that's just upper bound and lower bound. Now for the supremum, if you have a set S that's bounded above, U is called the least upper bound, or the supremum, if and only if U is an upper bound for S. And if B is any upper bound, so underline stress any upper bound for S, then U is less than or equal to B. And then the infimum, similar thing. If you have S bounded below, B is called the greatest lower bound, or the infimum, if and only if B is a lower bound of S. And then if C is any lower bound of S, again, any, then C is going to be less than or equal to the value B. Those are the formal definitions. Let me draw a picture. All right, so let's say that's my real numbers, and I'll let our set A be this. And let's see, so we're going to use the letter U for the supremum. And then I'll use the letter V for the infimum, which is the greatest lower bound. And so I use I and F of A for infimum. Now, based on our definitions, so let's take a look at the first one for supremum. So use an upper bound for S, and if B is any upper bound, U is less than or equal to B. So any of these values, these are values B. U is upper bound of A, and then U is also less than or equal to all the other upper bounds, or any upper bound of A. And then for the infimum B, are values that are lower bounds of A, any of these values. So these are like my values, C, and the infimum V is the infimum if V is greater than or equal to any lower bound of A. And I have it in the definition C less than or equal to B, where C is any lower bound of A. Okay, so that's formal definitions. Now, the real numbers is complete means that every subset of the real numbers that's bounded above has a supremum that's in the real numbers. And I put in parentheses the supremum and it's unique. So for a theorem, let S be a subset of the reals be bounded above, then the following are equivalent or following hold. Our first point A is that the supremum is unique. The second point is that if U is a supremum S, that's if and only if S is less than or equal to U for all elements S in the set S. And then if V is less than U, then there exists an element S in S where V is less than that element in S. And then the third bullet point, so let U be an upper bound of S, then U equals the supremum of S if and only if for all epsilon greater than 0, there exists an element S in S where U minus epsilon is less than S. So I drew pictures representing this. This is the case that's representing C. So this example. All right, so for my example, S is the pink values, and I drew it as a vertical line. I mean, it's just one line. Sometimes I'll draw it vertically, sometimes I'll draw it horizontally, or set S. So let's see, that's the real numbers. Our set S doesn't have to be just a simple open interval. Like I could have something like this, and it jumps like that. So this, I could have something like that as my set S, which is what I drew over there. Now, the supremum, and first off, all of this is the upper bounds of S. I'm drawing a similar thing, just it's horizontally. And the supremum U, say that's U. So is the supremum if and only if for all epsilon greater than 0, there exists an element in S where U minus epsilon is less than S. So let's say we have epsilon subtracting from U. That's going to put us something like that. And then you'll see that there are values in S. So we have, these are my values in S, where S is greater than the U minus epsilon. All right, that's demonstrating the third bullet point just as a picture. And they're both the same. I just wanted to emphasize two things. You can have a vertical line as a picture representation. Also, the set S can be something weird where I have it like jump like that. Earlier, I was just having the set A be just a simple open interval. But our set doesn't have to be like that. Now for the second bullet point, I drew the following right here. So use the supremum, and again our set S is this pink stuff where it sort of jumps a couple in different parts. But U is the supremum if and only if for all S in S, S is less than or equal to U. Well, that's certainly true. Everything in pink is less than or equal to the yellow part of the line. And then if there's a value B that's less than U, so that's where B is, if that value is less than U, then there's some value S in between. So there's some value S such that B is less than that value S, which is less than U, less than or equal to U. All right, so that covers that theorem. Here are just some examples. The supremum doesn't have to belong in the set, and the same thing for the infimum. So infimum. So if you have the open interval from 0 to 1, the supremum is going to be 1, but it's not part of the set since it's an open interval. The other examples, it's just the open around 0 but closed around 1. In this case, this set contains its supremum. They have the same supremum as 1. One of them contains the supremum, one of them does not. So the real numbers is an order field that satisfies the completeness axiom, meaning that it satisfies the least upper bound property. And I know I'm kind of repeating a lot of the main points, a lot of the main stuff here, but the least upper bound property is if you have an ordered set S, like the real numbers, S has the least upper bound property if given any subset A, where A is non-empty, and A is bounded above, then A has the least upper bound. And particularly the supremum sup of A is that least upper bound, and it's an element of the set S for every such set subset A. And the real numbers has that property, satisfies that property, and that's called the completeness axiom. And I wanted to end the video with something like this, where we talk about the Archimedean principle. And the Archimedean principle will be used very frequently in examples where I do proofs. But we're going to end this video by doing the proof of the Archimedean principle. So the Archimedean principle says given any real number R, there exists a natural number where that real number R is less than the natural number N. I wrote in green the negation of that statement, and the negation of that is if there exists a real number R such that for all natural numbers N, we have N is less than or equal to that value R. That is the negation of that statement. And that's going to be important because when I do the proof, I'm going to do a proof by contradiction. All right, so we're going to assume to the contrary that there is that negation part, that there exists a real number R. All right, so contradiction proof, we're going to assume the Archimedean principle, that statement's not true, which that means then we're assuming that there exists a real number R such that for all N that are natural numbers, we have N is less than or equal to R. But since this holds for all natural numbers N, that means the natural numbers is bounded above. So this means, since this is holding for all N, so this means the natural numbers is bounded above. All right, so I'm going to let U be the supremum of that natural numbers. And we know that exists by the completeness axiom. Since the natural numbers in this contradiction proof is going to be bounded above, we know that if it is bounded above, it has a supremum that exists in the real numbers. So this supremum, U, is an element of the reals by the completeness, or at least upper bound property. And since this has to hold as far as our supremum, well, we know for a supremum, we know we use a supremum of some set S if and only if for all epsilon greater than 0, there exists an S in S where U minus epsilon is less than S. All right, that's just based on what we talked about earlier. So if that's the case, to make things easier, since this has to hold for every epsilon, I'm going to pick epsilon to equal 1. So that means there exists a natural number such that u minus 1 is less than that particular natural number. All right, so I use the fact that the supremum is if and only if there, for all epsilon greater than 0, there exists an element in the set such that u minus epsilon is less than that element. So I'm picking epsilon to be 1 since this has to apply to all epsilon. So that means since u is a supremum, there exists some natural number n, because our u is the supremum of the natural numbers, such that u minus 1 is less than this particular natural number n. Well, that means if you add 1, you'll have u is less than n plus 1. All right, so our u is less than n plus 1. But n plus 1 is a natural number, right? Just adding 1 to a natural number is another natural number, since the natural numbers are inductive. But hold on, we said u is a supremum. But u was supposed to be the greatest lower bound to the natural numbers. Or sorry, the least upper bound to the natural numbers. Yet we've produced a value n plus 1 yet we found an n in the natural numbers where our upper bound u is less than n plus 1. So that contradicts u being an upper bound. And our n plus 1 is an element of the natural number since n is inductive. So this contradicts u being an upper bound. All right, and that completes the proof. All right, that's contradiction. Therefore, it's got to be that the Archimedian principle holds. All right, so that's where I'll stop it for this video, and next video I'll try to do some examples of infimums and supremums.